very glad to have this chance to present my recent work. Most people in this room interested in the human evolution, but we are interested in the evolution of the human civilization. So some slides in this talk come from the Professor Chung Zhang in Stockholm University. We have a very close cooperation because she's my wife. Okay, I would like to, I'm trying to answer these two questions during the past 10 years. The first one is there natural centennial to millennial oscillation in the climate system? The second one is this variability connected to the evolution of human civilization? In today's work, I can only answer the first questions. Let me show some background. This is temperature and CO2 evolution during the past 400 million years. We focus on this time period, the past 10,000 years, the Holocene period. You'll notice that the temperature and the CO2 are very, very stable. So we are actually interested in the internal variability during this period, particularly the natural variability at a time scale of the 500 plus minus 300 years. So if we look at the whole spectrum of the Earth's climate variability, you'll notice that there's a multi-centennial peak here. But this peak is much smaller than the climate variability of the other time scales. I think this is one reason that this time scale variability is very few studied. So what about so why we are motivated to study this kind of variability? Because there's a lot of the observations showing multi-centennial variability. This work from the Toms, he examined the Holocene practice data. You can see the data over land and ocean, and also a lot of practice data in China will show this kind of this kind of variability. So we also, I also examined a lot of the previous studies, and you see the tree ring data and basin sediment data and the oxygen isotope data. They all have the multi-centennial peak. Particularly the data around the North Atlantic Ocean. And the documentary record in China shows that there's a 200 to 300 years periodical change in the eastern China wintertime temperature during the past 2,000 years. This temperature evolution is in agreement with the change of the dynasty in ancient China. The warm period we have the Donghan dynasty. Cold period we have this kind of period. Also, you can see the Little Ice Age. Very cold period, lasts 300 years. Actually, this kind of periodical change occurs in the whole past 5,000 years. So, of course, there's a lot of scientists in China study this kind of documentary record and this kind of history climate change. And Professor Zhu Kezhen proposed that during the past 5,000 years, there's about two time scales. One is 200 to 300 years, and another one is a 600 years period. So this is the most recent work by Professor Chen Hai in Xi'an Jiaotong University. He found the 550 years period variability over the Yunnan Guizhou Plateau during the past 700 years. He related this kind of variability to the AMARC. So so the climate system does have the multi-centennial variability. And so our next question is, what component of the Earth's climate system can provide this multi-centennial timescale? So because I'm an oceanographer, I think the Great Conveyor Belt, particularly the AMARC, has a timescale of 1,000 years. They can provide the multi-centennial timescale. But you know, the decadal and the multi-decadal variability in AMARC has been provoked by modern instrumental observations. There's no direct evidence for the multi-centennial variability. So we have to rely on the couple models. There's a lot of the couple models showing this kind of variability, multi-centennial variability. For example, this is a 2,000 years PI control run from the EC Earth model. They have a peak about 200 years. And the model study from the Germany scientist and from the French scientist. And we also have a very long simulations, 2,050 years long simulations with the NCAR-CSM model. We found 300 to 5 years period in the AMARC index. And they also have, the Arctic sea ice also has this kind of the variability. They have, Arctic sea ice has a very good correlation with AMARC index, but we don't know the causality. So 5 years ago, we decided to decipher this mystery. So we have observation, we have couple model. I think to answer the why and how, I think the theory is extremely needed. So in terms of theoretical studies, there's a lot of the theoretical study on the AMARC from the simplest two-box Stormer model to one-box Wielander model and three-box Roos and Wielander model. I'm not going to go through these details. Let me just jump to summary. So the previous theoretical study on AMARC focused on its stability, bifurcation, and regime shift. There's no theory on the multi-centennial variability and the stable climate. You know, the climate variability that ocean matters includes the ENSO, PDO, and AMARC. They all studied comprehensively, but there's a very few study on the multi-centennial timescale. So we would like to search an eigenmode of the multi-centennial climate variability in an unstable climate. And we also like this mode to be self-sustained. So what is a self-sustained eigenmode? You know, people know the unstable mode and damper mode or neutral mode. A self-sustained mode is growth from the it grows first and then sometimes it reaches a stable state. So you can see that the self-sustained mode can be only transformed from the unstable mode. So let's see the theory we built. We use one hemisphere 4-box model. This box model has 2 layers, and this is a tropical box, and this is this is a tropical box, this is a subpolar box. The blue arrow represents the AMARC. So if we have an extreme mixing or convection in the subpolar box, the 4-box model can be reduced to the 3-box model. 4-box model have 4 equations, 3-box model have 3 equations. The 3 equations can be solved theoretically because we have another condition that is total salt conservation. So 3 equations can be further reduced to 2 equations, quadratic equations. So the theoretical solution can be easily obtained. Here we assume a linear closure mass between the AMARC and the Meridional density gradient. the lambda is linear critical parameter. This lambda is very, very important to control the oscillatory behavior of the AMARC. And this is a theoretical solution. So the real part of the solution gives the stability condition of the system, and this part gives the oscillation condition of the system. If this is positive, we have a growing oscillation. If this is negative, we have decayed oscillation. The value under the square root, if this is positive, we don't have oscillation at all. Only this is negative, we have oscillation. So finally, we found the eigenmode with the time scale of the multi-centuries here. This is lambda. I'm not going to go to the details. So this figure shows the mode, the dependence mode on the lambda. We have damper regime because we have a negative real part of the eigenvalue. This is unstable regime. We have because of positive real part. This is self-sustained regime. And when we include how to realize the self-sustained oscillation, when we include the enhanced mixing or convection in the subpolar box, another term, so we can finally get a self-sustained oscillation of the system. Like this, unstable mode can be transformed to the self-sustained mode. Because this box model is too simple, so each process can be clearly identified. So we also did a lot of sensitivity experiments on parameters to study how the parameters and the basin size affect the self-sustained mode. So we found a damper regime and unstable regime, and this is a self-sustained regime. So under the reasonable climate parameters, the self-sustained oscillation can be easily obtained. You may notice the small star. This shows our current climate background. So this self-sustained oscillation can be also forced by stochastic forcing. We use white noise forcing. We got the AMARC response. The AMARC has a clearly 300 years peak here. So this confirms further this mode is the eigenmode of the climate system. So what about the couple models? Okay. So we are very lucky to the process study in the theoretic model is verified by two couple models. The first one is the easy Earth couple model. You see the AMARC index has a 200 years peak. So this Hofmode diagram shows the salinity regression on the AMARC anomaly. You can see in the upper ocean, the salinity anomaly developed locally in concert with the AMARC anomaly. This plays the positive feedback to the AMARC anomaly. This is completed by the perturbation at the vacuum term. In the deeper ocean, in the lower ocean, you see the salinity anomaly can be propagated southward. This propagation tends to remove the anomaly in the subpolar ocean. This plays the negative feedback is completed by the mean at the vacuum term. This is the Meridional section of the salinity anomaly. You can also see the local development of the signal and the vertical mixing and the convection very clear here. This is the result from our CSM model control run. So we got a 350 years period. You can see the multi-centennial variability is most significant in the subpolar Atlantic. This is a Meridional section of the salinity regression on the AMARC anomaly. So you can see the local development in the subpolar ocean and the vertical mixing, convection, and the southward advection is very clear, shown in these figures. In the upper ocean, the salinity developed locally. This is the positive feedback. And in the intermediate ocean, the salinity propagated northward tend to cause the phase shift of the multi-centennial variability. In the deeper ocean, we see the southward propagation of the anomaly, which tend to remove the initial perturbation. So the process study in the carbon model is exactly predicted by the theoretical model. So 3 terms. One is the positive feedback by the perturbation advection. Another one is a negative feedback by the mean advection. The third one is also negative feedback by the vertical mixing. And this is 3-dimensional diagram showing the dynamics. I'm not going to the details. Finally, we spent about 10 years trying to answer the questions. So, because there's a centennial variability found in the product data and the carbon model, so we propose this theory to explain this variability. So, understanding the human civilization, what can we do? So I think the first, we still need fundamental theories. This has been done in the past several years. The second, we are working on this carbon modeling of the global climate evolution during the past 5,000 years. This is to obtain the background climate. The third, we think we need a downscale modeling of the climate and even weather in particular regions. This is to obtain high resolution data. After we have this kind of data, we can make stories. And I think the great challenge, there's a great challenge in the future, how to explain the evolution of the human civilizations. This so depends on how we make stories. So in summary, I have a very bold assumption that is during the period of agricultural civilization, the evolution of the dynasty in ancient China might be determined by the evolution of the natural variability, particularly the evolution of the ocean subhighland circulations. I think I stop here. Thank you very much.